this video, what I'm going to be talking about is the periodic table. And just as a quick introduction, if you see for each box that each element exists in, there are three different important pieces of information that you will find. You will find the atomic number, you'll find the atomic symbol, and you'll find the atomic weight. Remember, the atomic number is the number of protons, the symbol is simply the symbol, and then the atomic weight is the weighted average of the atomic masses. So here's your periodic table right here, and just as a quick review, remember that the periods represent the horizontal rows, while the groups represent the vertical columns. The next piece of information that you need to know is that there are three different types of atoms that you can have. The first are metals, and so if you look, all of the elements that are in brown, those are your metals. Now, there are a couple of important pieces of information about metals that you need to know. Metallic elements, they are lustrous. They have luster, meaning they're shiny. They're good conductors of electricity and heat, and they're also solids at room temperature. So notice most elements on the periodic table are actually metals. So what I would do if I were you, the periodic table that I gave you is actually the periodic table you'll have on the AP. So I would color in addition to the charges that you just wrote, I would also color in the metals. Then the metalloids, those 6 elements, those share both metallic and also non-metallic characteristics, so that's why they're in between the metals and the non-metals. Now, the green elements, those are your non-metals. Notice all of them except for hydrogen are to the right of that ladder, to the right of the metalloids, and they are either gases, solids, or liquids at room temperature, and all of their other characteristics are opposite of that of metals. So for example, they are not lustrous, they are not good conductors of electricity. And then you have your metalloids. The next thing that we're going to be talking about is molecular compounds. Now, molecular compounds are created by having 2 nonmetals bind together. Now, the way that they're bound together is through a covalent bond, and a covalent bond results from the sharing of electrons, which we'll look at a little bit later on. Now, there are 2 different types of formulas that you can have for molecular compounds. You can have a molecular formula, which represents the actual numbers of atoms in a molecule, versus the empirical formula, which indicates only the relative number of atoms. So it's the smallest possible whole number ratio. Well, the question is, well, why would you have an empirical formula? Why not just the molecular formula? Well, if you have something like C2H4, that is the molecular formula. Now, if I wanted to know, for example, for every 1 carbon, how many hydrogens do I have, that would be your empirical formula. So your empirical formula is the formula that has been reduced to have the smallest possible whole number ratio. And we're going to be looking at how to calculate your empirical molecular formulas later on. When we're dealing with covalent bonding, we have to use prefixes because we have 2 nonmetals. We don't have a metal and a nonmetal. Okay, so the prefix tells you how many atoms you have of a specific element. So for example, mono is 1, di is 2, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. So let's look at an example. Here I have CO, so I know I have 1 carbon and 1 oxygen. The only additional rule you need to know is you do not start the name of a compound with mono. So instead of monocarbon, because there's 1 carbon, I'm just going to write carbon. And then I do have just 1 oxygen, so it's going to be monoxide. Now to write the formula, I simply have to use the prefixes. So this is carbon tetrafluoride. So carbon, I have 1 carbon, and then I have 4 fluorides, so it'd be just CF4. Now the other thing that we need to talk about, now that we've talked about molecular compounds, is we need to talk about ionic compounds. But in order to talk about ionic compounds, we need to talk about what happens when atoms, instead of sharing electrons, when they actually lose or gain electrons. And what forms when atoms lose or gain electrons is ions. Now, if you have a positively charged ion, that is a cation, while a negatively charged ion is an anion. And so what happens, for example, if sodium were to lose 1 electron, it would have a charge of +1. Now, chlorine, if it gains that 1 electron, it would have a charge of -1. And so what you need to know is that metals tend to lose electrons and they therefore become cations, while nonmetals gain electrons to become anions. And so that's why if you have an ionic compound, it's between a metal, which lost the electron, and a nonmetal, which gained the electron or electrons. Okay, and the last important thing for you to know is that the chemical properties of ions, so for example, sodium ion is very different from sodium atoms. Sodium ions exist in your body, while sodium atoms, they react extremely exothermically. They actually explode if you put them in water. So those are not in your body. It's the sodium ions that are in your body. And so if you look here, this is an ionic compound, and it results from the transfer of electrons, so you'll have a positive and a negatively charged ion. Now notice that the positively charged sodium ion is going to be surrounded by chloride ions completely. So when we're talking about ionic compounds, you don't actually have just one molecule. Instead, you have billions of sodium ions and chloride ions that surround each other in this very nice structured form that's called a crystal lattice structure. And so that's why salt looks like crystals, because they are crystals. And so we don't use the term molecule if you're counting the number of molecules. You use that term when you're talking about molecular compounds, but for ionic compounds we talk about formula units, simply because you're not going to just have one molecule of NaCl. Instead, you're going to have this huge crystal lattice structure. So an important thing for you to know is that when ionic compounds form, their overall charge is going to be neutral, and so that's going to help us when we're writing out the empirical formula. Now note, ionic compounds do not have a molecular formula, because if you have, for example, NaCl, you never write Na3Cl3 if you had 3 of each of them. That you're not going to just have 3. The empirical formula for an ionic compound is the only formula we have, because for every one sodium ion you have one chloride ion. So while you'll have molecular and empirical formulas for molecular compounds, you will not for ionic compounds. And so when we're writing the formula for an ionic compound, you're going to take the two charges and you're going to cross them. So the 2 from magnesium becomes the subscript for nitrogen, and the 3 from the nitride ion becomes the subscript for magnesium. And the reason why you do this, if you look, magnesium has a +2 charge. And so if you have 3 magnesiums, that would be a total charge of +6. Nitrogen has a -3 charge, but since you have 2 of them, that would be a -6 charge, and so their charges actually cancel. So the concept of crossing charges makes this creation of a neutrally charged compound very easy for you. So if you look at this example, you've got sodium sulfide. So sodium has a +1 charge. Sulfur, or sulfide, has a -2 charge. And so when you cross your charges, what you're going to get is Na2S. Now the last thing I'm going to be talking about is actually naming the ionic compound. So now we're not going to write the formula, we're going to name it. And so if you have an ionic compound, you've got 2 situations that you can be in. The first one is if you have a cation from a metal whose charge you know. So for example, any group 1, group 2, or group 3 metal, you know its charge is always +1, +2, or +3. And so I do not need to include the charge of the metal when I'm writing the name. However, if I have a metal whose charge I do not know or can have different charges, specifically your transition metals, then you need to represent the charge as a Roman numeral. So for example, iron, if iron had a 2+ charge, you would represent it with an iron with a Roman numeral 2 behind it in parentheses, and then you would continue on just like before. And then for example, for iron 3, it would be iron with a Roman numeral 3. So that's for the cation. For the anion, what you do is you simply write the name of the monatomic anion, and then you add an IDE ending. So instead of chlorine, it would be chloride. But let's actually look at some examples to make sure we understand. So manganese, in order to not write the Roman numeral, I need to know the charge of the metal. Well, I know the charge of group 1 and group 2 metals, and I also know the charge of aluminum. I don't know the charge of my transition metals. So manganese, I don't know the charge of. So since sulfur has a -2 charge, that means manganese needs a +2 charge. So it's going to be manganese, and then I've got to write 2, and then sulfide. All right, let's look at one more example. If I give you CaF2, well, calcium's a group 2 metal, which means I know its charge, it's +2, which means I don't need to include the charge in its name, so it's just going to be calcium fluoride. So now let's look at the last type of naming that I could possibly do, and that would be with your polyatomic ions that, remember, you need to memorize. Okay, so with molecular compounds, remember you use your prefixes to name them. For ionic compounds, you just write the name of the metal and the nonmetal. But if you don't know the charge of the metal, you need to use a Roman numeral after it. For both of those, you add an IDE ending to the nonmetal. Okay? However, for polyatomic ions, if you look at this one right here, you're not going to put an IDE ending. Instead, you're just going to write the name of the polyatomic ion. So for example, if you have Na3PO4, I'm just going to write out the name. Now, do be careful because this is an ionic compound, okay, because you got a metal and nonmetal. Then I need to see if I know the charge of sodium. Well, sodium's charge is +1, so I know its charge because it's a group 1 metal. So its name is going to be sodium phosphate. Now, if I give you the name of an ionic compound that has a polyatomic ion, for example, iron 3 hydroxide. Okay, notice, because I don't know the charge of iron, because it's a transition metal, I needed to include that Roman numeral. So iron has a 3+ charge. Hydroxide has a -1 charge. So I'm going to cross my charges because this is an ionic compound. All right. And so there'd be a subscript 1 for iron, so I'm not going to write anything, and there's a subscript 3 for hydroxide. Make sure, however, if you were to write FeOH3 and that's it, that means you have 1 oxygen and 3 hydrogens, and that's not correct. You want 3 hydroxides. So the way you would write this compound would be FeOH in parentheses 3.